Does anybody have any other questions in the meanwhile? Well, about any of the content they've studied so far in the course. I have one question that somebody asked. I'm going to go over that super quickly. But if you have any more, just let me know. Don't be shy, please. Yep, awesome. So we can wait until after the session to go over that particular question that you have, and that's very nice of you to wait for everybody, and not mess it up. So yeah, we'll to finish up our discussion today. Hopefully we answer that as we go, but if not, then we'll cover that up too. Okay, I guess this is time to start. What I'll do is I'll give you an opportunity to try to guess yourself how you're gonna start to solve an integral. If I'm gonna give you a quadratic, okay? And today is basically wow. You can't even draw a straight line. Look at me. Okay, awesome. So we're gonna start to eventually, put out some context to the problem first. Like, what is the deal with quadratics? Like, why are we looking at them specifically? Why don't we look at getting cubics? Why don't we look at any other functions? Why just quadratics by itself, right? So the context here goes as like this. So we're gonna start off by giving it an integral, which you're gonna solve, and I'm pretty sure everybody can do it now. So that integral will be.
Little does he know Claire cannot do it.
So that is an integral in front of you, and supposedly you can say this is a quadratic there too, right? How would you take an integral of that? And the stage is open in the chat. You can try to tell me how you would want to do that, and I'm pretty sure everybody knows it, but I just want to make sure that we're all on the same page. Anybody who would want to say like they see something suspicious in this integral, or no? Okay, let me ask the question in the other way. What I'll ask is like, let's see, does everybody understand why this is okay as the answer? A little yes in the chat would be good, so I know that everybody understands that this is the integral's answer, right? So everybody agrees with me on this. Okay, so now I'm gonna make it a little bit complicated. Okay, a little bit complicated, where you would have to do an extra step in order to just kind of get it out of the way. Okay, and that integral will be this. So if you're keen and you have a good eye, you already know that these two things are exactly the same. One is just expanded, the other one is just going to be condensed into one form, right? So then taking the integral of this x plus 2 whole squared, how does that differ from there? So the answer should be exactly the same. You can expand and do it. That's completely valid. But because you've been studying a lot and you've been following along with the chain rule of integration we talked about, in that chain rule of integration, we would have seen that this integral will be done by having a linear plugged inside a squared function. So you can treat it as that thing plugged inside a linear function. Take the integral of the outside function, and then you would have to multiply by the divide by the derivative of x plus 2, which happens to be just 1, so that is the answer. Right? So now, this is exactly the same integral is going to give you exactly the same answers in both the cases, right? The way you expand it, you'll get the same exact result. One form of a quadratic is here, the other form is here. So I'm going to label that option number 1 and option number 2. Okay? For the same quadratic, which one do you prefer to work with in this particular scenario? Do you think integral number 1 was easier or number 2 was easier? Okay, I have a vote for 1. Like, relatively speaking, right? I know both of them are easy for you because you guys smart, but just relatively speaking, 1 is always easier in your perspective, right? So that's good. So when you're seeing a quadratic in this format, it will be easier for you to work in the expanded form, which is nice. However, if I do just one slight modification and do nothing extra, I'm just gonna take whatever I was having in the quadratic and put it in the denominators. And now you might want to see which option would you want to pick to integrate, because it's the same quadratic. It's exactly the same integral. It's just written in two different forms, right? Now, intuitively speaking, what do you feel which is going to be a little bit easier to solve? The A version or the B version? So I have a vote for B. And you guys kind of see why you want to lean towards B, right? Because you kind of don't have any way to go from the A version, right? And if you know, then please enlighten me at the same time, you know. I'm more than happy to learn as you guys, you know, learn with me. So it's going to be a harder way to kind of like work on this. But integral in the B version would have been super easy because you can use it as, you know, call it as x plus 2 to the power of minus 2. And the integral of that will be x plus 2 to the power of minus 1 divided by minus 1. Right? And you're done. So the idea that I wanted to get across in this whole scenario was that sometimes some forms are easier to integrate than the other in the case of quadratics. Okay? Now you've seen a live example. I'm going to give you one more complication of it, and then let's see if you can decide which one to pick with, okay? I'm going to take the same quadratic and put it inside a square root now, because I'm just playing with them, right? I have x squared plus 4x plus 2. Hold up. Did I mess up? Yes, I messed up over there. My bad. This quadratic should have a 4 there. Else it won't be a complete square. So I'm just going to go ahead and pretend that I did not make a boo-boo. Yes. Now it's more. No, oopsie. That should be 2. See, my brain's already farting. That should be 2 in the form, but in the expanded form it should be 4. Right, so that is okay to be this way. Yes. This makes more sense. Okay. So if that is a quadratic that you have inside a square root, you can have the same quadratic in the form like this. Now again, I ask you the question. I should insert that the meme there, you know. Once again, I ask you, A or B, which one would you want to integrate in this particular case? Form A, form B. So I have a vote for B. Does anybody want to go with the form A? Or does anybody know how to integrate form A? Okay. One person voting for A. So I would want to ask a little bit, how would you want to integrate the form A? because it's a function inside a function, right? And usually when we're working with those kind of scenarios, we want to use substitution. And then we already had a session on it too, so we asked like, do we have anything to help it substitute? Well, that thing is not linear, so we can't just go ahead and do it, so we need to figure out what do we need in order to get the substitution carried on, right? Right? So we're gonna see how this things work out. So keeping that in mind, that you have x squared plus 4x plus 4 in there, its derivative is going to be 2x plus 4. So you need to have a 2x plus 4 with the dx in order to carry on this whole thing, right? To make the substitution happen. You don't have that here. So then option A is a no-no, because you can't really get out of it anyway, right? Does that make sense to the person who is supporting A? Yeah. So you're causing yourself trouble. So yeah. So in this point, you would want to go with U substitution, and you already know how to identify when a U substitution is there. It's good. It's an eyeballing game. However, integral B is so easy that you can just take the square root of square and just get this function. Right? And that way you will just be getting as the answer and call it a day. Very pretty, right? So we'll kind of like emphasize in this fact that you can do different versions of the same problem to get to the solution, and it's okay. They're not any different. We just want to be careful how we do that. Now that we recognize that there's some forms that are easier, some forms that are difficult, do you know how to go from one form to the other? That's the most important thing. In this case, I told you that x plus 2 whole squared and x plus 4x plus 4 are exactly the same. But can you do that for yourself? Can you change a quadratic into other forms? So we're going to discuss that first. Okay? So you have a quadratic. It could be changed in either of these two forms, okay? A quadratic can be either factor, like we did, okay? That quadratic in x plus 2 whole squared was basically factored to be in that form, right? And if not that, then this quadratic can be squared. And by that, I mean completed square. Okay? So these are the two things that how you can treat a quadratic and turn it into a form that you want to work with. You gotta ask yourself a question whether you can factor a quadratic or you can square a quadratic, right? So we're gonna look at a bunch of the examples and see if we can actually decide whether you want to go with factor or square. The rule of thumb here is very important. This pathway of completing it in a square form always works. So you can always square or complete square any quadratic in any form. Okay? That's very important. This is always true. But how about the other factor form? This pathway is sometimes. Okay? And sometimes when you're blessed. Basically, that's what it's going to be boiling down to. And you'll see. Factoring a quadratic leads to a method, and completing the squares will lead to another method. So that's what I'm going to say right now. Okay. The method that would eventually follow along, and I'm going to explain the method in just a second once we actually get there. The method that you'll follow along after factoring quadratics would be most probably partial fractions. Okay? This is an integration technique we're going to talk in detail about. Okay? But that's how the pathway flows. Once you have a quadratic, if it's factored, you can apply partial fraction decomposition to it because it requires to have factored polynomials in order to apply it. Okay? But if you cannot, which will be the case most of the time, right? If you want to do it that way, if you cannot factor it, then you want to complete the squares, and then completing the squares will lead to the method of trig substitution. Okay? This is kind of like the breaking point here. So, as we just kind of have this logically said that you can always complete the square of a quadratic, well, hence, you can always turn this into a trig sub problem. You know, because every problem could be done into a trig sub problem. But because people hate trig so much, you know, nobody likes sine, cos, and blah blah blah, and you know, it just makes them feel weird. That's why we have this simple method that sometimes when we're blessed to have a factored polynomial, we can go sideways and do something easy. If not, then we have to suffer through this pain of trig substitution every single time, right? So that's the basic idea of what we're going to talk about today. We have to be able to decide whether we're going to be able to do partial fraction decomposition or trig substitution in each one of these cases, right? So they could appear in all these forms, you know, sometimes in square root, sometimes in denominator, sometimes in square roots inside denominator. So they could be like a mix and match of all those things. But eventually the idea stays the same, right? You have to recognize which form would be helpful. And once you recognize what form will be helpful, you can apply the rules very easily. Okay? So let's keep that in mind and let's try to work that way through. So I'm going to write like a bunch of quadratics and ask you guys if you can factor them, right? If you can factor them, good. If you cannot, then you have to square them, right? So that'll be a good opportunity to reflect back on, are you able to factor quadratics? I'm pretty sure you are. And at the same time also learn the pre-calculus way of completing the square. Or some of you guys might have learned it as writing a parabola in a vertex form, you know? That way is also the same kind of idea that you work with. I'm going to show you that. It's going to refresh your memory, right? So a bunch of quadratics I'm going to take straight up from your homework. You know, that's going to be the cool part. So I'm going to try to go there. Let me open that up. Yes, so have them from the homework, yes. So question 4 in your web work has a quadratic that says 64 minus 81x squared in my version. Okay, that is a quadratic that we see over there. I see another one. I see question number 6 has a quadratic saying 25 minus x squared. And that's a trick question. Question 7 in my version has a quadratic which is x squared minus 100. And then question 8 has a quadratic which is 45 minus 108 x minus 81x squared. And that's about kind of it, you know. I'm just going to take one more 9. Question number 9 has a quadratic that we have as 1 over. Not maybe 1 over. I'm just going to look at the quadratic for now. So you got all these bunch of quadratics specifically in this 12 question web work that you have, right? Of course, we're going to go over these questions and discussions on the next time we meet. Today is only for the talk about the theory and give you a chance to apply what you learn here today into those web works, right? So these quadratics are specifically made for you so they cannot be factored. Because this question is trying to aim towards trig substitution. Now it will start to make sense that why you cannot factor these quadratics, right? And I'm guessing the web work right after this particular case, you know, web work 8, will be on partial fraction decomposition, right? So it's going to be like a whole new class over there, right? So before we go there, these are all the quadratics that are specifically made, which will need to be in completed square forms. So let's try to see which ones are completed square forms. A completed square form okay, in general, will always look like this. Okay? Will always look like this. This is what we want to convert every quadratic into. Where we have some constant a times x plus b whole squared plus c. Okay? And you want to identify what a, b, c are, you know? So we're gonna try to tell you how to do that in a very naive way, very typical way. And how you do that is by reverse engineering things, okay? So let's try to see. Let's expand this out. Once you expand this expression out, you would get ax squared plus 2abx plus the b squared a plus the c, right? This is how you would have your generic quadratic expanded out in that case. So now if you want to compare and find the a, b, c equivalent of any of the given quadratics here, you would be very easy to do that. Okay, let's pick this example. Let's see you want to convert this form into a completed square. So if you write them like this, right underneath each other, you'll be able to compare them very easily. So this quadratic rewritten in a nice way will be like this. Alright, so here when you compare these things, you can deduce conclusions right away. Because the x squared terms should match up, right? Once you want to match up the x squared terms, you will be like, okay, then that makes sense to have a be equals to minus 81 in this particular example, right? And if a is minus 81, you also know that 2 times a times b must be equals to negative 108. So when you do that, you have 2 times negative 81 times b equals to negative 108. Then you realize that b just needs to be equals to, I'm going to cancel the negatives, still just going to go away. So you have 108 divided by 2 times 81, right? So comparing the x coefficient gives you the value of b. And now you got to compare the remainder part of everything, that's 45, to get you the value of c, right? So now if they're comparable, then what b squared a plus c is going to be equals to 45. So we know b is this, so you're going to have b squared, so it's 108 over 2 times 81 whole squared times the value of a, which is minus 81, plus c must be equals to 45. So hence c must be equals to 45 plus 81 times 108 divided by 2 times 81 whole square. So you've basically found out the ABC value. Now all you got to do is just put it back in this form, right? Does anybody have any questions about how I know these numbers are hideous, and that's not the really point of the whole thing. I'm going to try to do the one for the easy x squared plus 8x plus 52 as well, but I'm going to show you the example. But do you follow along the methodology to be able to convert any quadratic, which is written in the expanded form, into a completed square form? Right? To put it in the completed square form, you have to find these Lego pieces of A, B, and C, and this is how you find them. You write the quadratic right underneath the expanded format of this, compare these two guys, and then build back your formula. Right? This is a bulletproof way of working through it, and this will cover up all the spectrum of things that you guys have learned before too. Okay, which is good. I'm happy that this was a good explanation, right? If anybody has any questions at any time, please ask me. I'm going to do the same procedure to convert this guy into a completed square form, right? So let's go that on the next page. So I know the completed square form should be a x plus b whole squared plus c, right? I'm just looking for ABC. So I'm going to expand this out. I'm going to be like the ax squared plus 2abx plus ab squared plus c, right? So now I'm going to write the quadratic underneath it, so it's going to be easy for me to compare that. X squared plus 8x, and all of that constant is going to be plus 52. So far so good, right? By comparing these two guys, you can easily deduce that a needs to be equals to 1, because the coefficient of x squared is 1. And now if a equals to 1, then twice times 1 times the b value must be equals to 8 when you compare these guys together. Right? And this simply implies that b needs to be equals to 4. right? So these numbers are nice. So when b equals to 4, then you go back to the last conclusion of yourself. You say, okay, ab squared plus c equals to 52. That means 1 times 4 squared plus c must be equals to 52, implying that c must be equals to 52 minus 16. And now I'm going to put some extra pressure on my brain and do the mental mathematically. So 50 minus, 16 would give me 34. And plus 2 would give me 36. See, I'm a god at math. I can do that in head, so it's 36. So far, we found out all these numbers. So now, to put this into its alternate form, I'm just going to take these ABC and rearrange it like this. So it'll be 1 times x plus 4 whole squared plus 36, which essentially is just x plus 4 whole squared plus 36. Does everybody understand how I went from this form to that form? Right? There shouldn't be any questions now in this. If they are, of course, you're more than happy to ask them, Does that make sense to everybody? Right? Okay, awesome. Cool stuff. Now we're gonna come up with the next gradual step, okay, of getting into the form and making sure that we're able to get to the results very easily. Okay, so now that we're comfortable comparing and like changing this stuff here and there, I want you to memorize. Of course, I can go talk about the literature behind it, but I want you to memorize 3 trig identities. Very important, okay? Only 3. And in this case particularly, I'm talking about the method of trig substitution and the motivation behind it. Okay, so you'll learn these 3 trig identities, and after like you do it a couple times, it will be a habit. Okay, it will be a habit that you want to make sure you understand and you remember them. Okay, and those are as follows. You need to remember that 1 minus cos squared of x is sine squared of x. I should t. I should use t in order to just make it very easy for you to just ingrain that in your brain. So 1 minus cos squared of t is equals to sine squared of t. That's number 1 that you have to remember. The second identity you have to remember is that secant squared t minus 1 is equals to tan squared t. So that makes 2 of them. The last one is very easy. It's just rearranged version of the first one. So then you would write this as tan squared t plus 1 must be equals to secant squared t. This is all I ask from you to remember, okay? Once you remember these, you'll be able to flow with these problems so easily and so intuitively that you would want to make sure, you understand this. Okay? So, does that make sense? These 3 are not too bad, right? So I want you to remember them symbolically too. I'm going to make some weird shapes and stars. Okay, to kind of show you the form, the symbolic form of what's happening. You have 1 minus okay, 1 minus something squared could be converted into some smiley square. Okay? This is that's the form of the second identity. And the form of the third identity does everybody see how like these symbolic forms of these things match up, right? Does everybody agree with me? That you see like when it's 1 minus something squared, you can convert it to something. When it's something squared minus 1, you can convert it to something. When you have something squared plus 1, you have to convert it to something. So now, effectively, we've covered up all the possible combinations of 1 and something squared being added or subtracted. Okay? The fourth redundant combination would be like 1 plus something, which is exactly the same as that, right? We have 1 minus something or something minus 1. Those are the two possibilities of negative. But a positive has only one possibility, right? So we've covered up kind of like all the cases you see here. Does that make sense? Awesome. Now is the time where we actually use all the silly Teletubbies math that we just did to actually solve something, right? Let's go back here. This was the form that we were working with, x plus 4 whole squared plus 36, right? I am trying to see that you guys can already see what I'm leaning towards. So it's x plus 4 whole squared plus 36. My job number 1 here is to make that 36 into a 1. Okay? And how can I do that? I can do that by factoring everything out of this, right? If I can factor 36 out of this will be 36 with so one of the portion is done, right? And now remember, in a symbolic notation, you want that star to be whole squared. Okay? You want that star to be whole squared. That's why the smiley will be a whole squared, right? Right now I have x plus 4 to the whole squared, but yeah, 36 is just kind of like odd. It's sitting in the middle. Can I do this? Am I allowed to mess up with math and do this? Am I committing a crime? Hopefully not, right? This makes sense to everybody? Because this is where everything is going to be grinding on. You know, when you do the examples, do the problems, this is the meat of the problem. Understanding these steps. Right, so I have 1 yes for this method. Does everybody else get it? I'm guessing yes too, right? Okay, cool stuff. So now I'm going to mess up and kind of convert all of this back into this standard form. Now you see the star in my case is what? Star in my case is x plus 4 divided by 6, right? And this looks like a symbolic form of x plus 4 divided by 6 whole squared, which is something squared plus 1, right? Now, wouldn't it be nice? This is where I want to draw the conclusion. Why do we even do trig substitution here? Is wouldn't it be nice if that something star is exactly 10, right? Because if that star is 10, that smile is secant. Agree or not? If that imaginary star that we just made over there was 10, then the smile will automatically convert into secant, right? So now, my job is to actually do that substitution and make that star into a 10. So why don't we do that? Let's do that here. So you have 36, the x plus 4 divided by 36, oh, by 6, my bad, whole squared plus 1. And now I'm going to do my substitution here. I'm going to be like, okay, let x plus 4 divided by 6 be equals to 10 of t. Right? And from there, you can kind of like isolate for x if you want to. That'll be equals to 6 tan t minus 4. And then from there, I'm going to isolate for my dx because I need to have a dx to substitute, right? So then from there, the dx will be equals to the derivative of 6 tan t. If you don't remember that, you can brush it up a little bit and be like 6 secant squared t with a dt. Because the negative 4 will have a derivative of 0. Doesn't really matter, right? So this is how I have my combination here helping us. Let's see how does that turn my problem into something easy or useful or something like nice. Let's see. So once that 36 placed here, we would make this expression into this. Right? And of course, I haven't put a dx there, but whatever there is a dx, this whole thing is going to go there, okay? For now, that's how the expression of the main quadratic got turned out to be. And now what else can we do? What else can we do? Can we use the trick that we just remembered to simplify it? Yes, we can. Because we know tan squared plus 1 is going to be equals to just secant squared of t, right? You can be like, this expression would just be equals to 36 times secant squared of t. So imagine, starting off, where do we start off? We started off at this position. We converted into this form. And then this form was kind of hard to work with, so what we did is we went ahead and just turned this into like a whole mumbo jumbo of just 36 secant squared t, right? And now I'm going to present you the original question that you had to integrate. You had to integrate. Let me just try to go that in the color like orange. The integral was this. If I'm copying it right. 52, my bad. This was the original integral. Now that all the math you did makes you realize that after doing all the substitution, your integral could be reduced into this very nice expression, where that quadratic could be converted into a squared form and then substituted by something trig to turn into this. Right? The function that we just had here. This guy, right? That's just the form of the whole same thing, right? And then dx was substituted to be 6 times secant squared t dt. Does everybody see how that integral got converted into something that we can call easy now? Do you see why it's easy? This was hopeless. You could not go anywhere. This question was out of the way. We could not solve this. Because if you can't factor it, you can't solve this pretty much. But now we've made a way that this looks so easy that this secant squared and this secant squared cancels out. This 36 and that 6 will cancel out to be a 6 in the bottom. And this integral effectively is just 1 over 6 integral of dt. God damn, that's the toughest thing out there, isn't it? Right? So the integral is just t over 6 plus c. And then you just gotta plug back what t is. We had the substitution right here saying that tan t is equals to x plus 4 divided by 6. So then t must be equals to tan inverse of x plus 4 divided by 6. So the final answer to this integral will be 1 over 6 tan inverse of x plus 4 divided by 6. Let's see. How about this way of solving integrals? So we have finished our first example of a trig substitution problem with the motivation built in. Yeah, everybody hates trig, but still, at the same time, this makes a little bit more sense, right? That why do we even care about this? So I'm going to refer back to these forms every single time when we do that. Okay? And I want to make sure that you understand the motivation of which one of you want to call what something. Like in this case, we wanted to call this a tan, or this substitution was a tan substitution because it was of this form. If something else popped up, it will be of a different form. And then in that case, you will have a different scenario. Integral will be different, but it will still be easier than what you started off to begin with, right? So I'm going to give you an example on one more problem. The one that we were looking at in the beginning. The 64 minus 81x squared. Okay? So let's look at this one. So you have 64 minus 81x squared. So my job here is to kind of like make sure that if you have something squared, whatever happening there, you should factor out to have a 1 there, right? In this case, first of all, I want to ask a question. Is this in a completed square form already, or you want to complete that thing? If you watch it really closely, this is kind of completed form. This is negative 81 with x minus 0 whole squared plus 64. Okay? If there's only one x squared in the term and no other x's, you've already got the completed form. So this is completed square. So you can go ahead and start to work your substitution method into this instead of just, trying to do it. Okay? So that is one of the things that I wanted to point out. We want to make that 64 into 1. That's the first religious thing I want to do to make this method, right, work. So what I'll do, I'll factor a 64 out of this. So I'll have 1 minus 81x squared divided by 64, right? So right now it looks like this. Right now the x is in the squared, but this 81 and 64 are kind of odd. They don't seem to fit well right now with the whole thing. I want to have one single bracket whole squared. So I'm gonna try to commit a crime, which is a legal crime in this case. Oh, can I write this like this? It just so happens to be that 81 is a perfect square of 9 and 64 is a perfect square of 8. So I can do that. If these numbers were not perfect squares, then I would just be silly. If this was, let's say, 65 instead, right? I would be like, square root of 65 whole squared. That doesn't really change anything. It's just that it's gonna look a little bit more hideous than it already is, right? Does everybody understand how, going back into this form and combining everything under the same branch works? Right? Awesome. So I'm gonna go back to 64 because I love nice numbers. And now you gotta go back to your memory lane and compare this to which form you want to work into this, right? So this is 1 minus something squared. Let's go back. You see 1 minus something squared, and that's the very first one, right? We have 1 minus something squared, turns it into a smiley, and that leads to a motivation that it will be very nice if that something is a cos of a function, right? So let's do that. I'm gonna call this cos. So this is where the substitution will come in. So you'll have 9 over 8x be called as cos of t, right? And then you can work your way. You have x equals to 8 over 9 times cos of t. And then you have dx being equals to, of course, from that expression, would be minus 8 over 9 sine of t dt. So this is like an extra piece that's hanging out there. We don't really need that for now. Once we have the actual integral, we'll do the dx plug in there. But right now I want to show you how this simplifies to be 64, 1 minus and then eventually, because we know 1 minus cos squared of t was just sine squared of t, this reduced up to be secant 64 sine squared of t dt. Okay? This is the whole expression after simplification. So a quadratic got turned into a nice trigonometric, not nice, but like a singular trigonometric expression, and that was good, right? Does everybody follow along with the substitution and the simplification of it, right? Okay, good. And now I'm going to present you the actual question. The question was there. The question in the rubric, which was question number 4, was this. The integral of dx divided by square root of 64 minus 81x squared. That was the original question. So now, we know 64 minus 81x squared could be written like this. So this integral is just 1 over square root of 64 times sine squared of t. And why do I have a dt there? I'm dumb. My bad. So now, the dx will have to have this dt over there. So I will have to have a negative 8 over 9 times sine of t dt. And now let's see, how does that actually work out? Is it even nicer to solve or no? I'm going to copy this, take it to the next page, and then I'll show you what I mean. So this expression could be written as 1 over 8 sine of t, because square root of 64 times sine squared of t is just 8 sine of t. Then you have multiplied by negative 8 by 9 sine of t dt. And you see this, that cancels out. This integral is just negative 1 over 9 of dt. And that's the hardest thing I've ever done in my life, but that's just how I was raised, you know? The integral of dt is t plus c. And then at this time you know how to isolate for t. Because you had this substitution made here, you could be like, okay, t is just equals to cos inverse of 9 over 8x. And you plug it back in, the final answer to this question is negative 1 over 9 cos inverse of 9 over 8x plus c. So this is how you tackle any quadratic that you have by using the method of trig substitution. How do you guys feel about it now? Does the method kind of make sense? The motivation should be in the place, right? And now, how that understanding that you just have will turn into a good, you know, like a solidified thing, is when we go over these questions in detail, right? So right now, a couple of days are your opportunity to try it out. And then if you can't figure them out, then we'll work over them together on Thursday, right? And because this thing is due on Saturday, am I right? Okay, the one work is due on Saturday, so I guess Thursday should be a good enough day to kind of cover up all these questions. They're not too bad. Last time when we met, we had to do both the things together because we only had one session, right? So that was like a longer 2-hour session. But usually I want to keep it short so I don't burn out your brains that fast. So this today was just talking about how to apply these methods. Second thing would be to kind of like go over the total thing afterwards once we're actually tackling questions. So you have fair enough opportunity to try it yourself. If you can't, then going over will just, you know, solidify that grind that you did. So that's one of the ways I want to do this. With the remaining of 10 minutes, I want to cover up today another type of questions that you might see in this case, which are the combination of tan and secant, and sine and cos, and blah, blah, blah. And you'll see probably rules online which says, okay, let's say I'm going to tackle this integral. It's a purely trigonometric integral. This doesn't have anything with quadratic, so that's off topic. But it's in this assignment, so I want to cover that up. I'm going to give you the motivation behind it too. So you have sine to the power of 8 times cos to the power of 3 dx, right? Usually when you're given these kind of questions, or in other words, maybe let's say, you know, integral of tan x to the power of 5 times secant 5 dx, right? So whenever you're given like these kind of things, you can kind of work your way around to converting them into something you can use up, right? So for this, you gotta remember a little bit of the rules that you would want to see. You gotta remember when you have a sine cos combination, the derivative of sine slash cos or whatever, right, is equals to basically right? These are the things. So you have to remember that they have a relationship of a derivative relationship, right? However, it's not that obvious in the case of tan and secant, so I want to show you the derivative of tan x is secant squared x. So that's one thing. The derivative of secant x is going to be secant x tan x. Okay? So those are like the memory things that you have to remember in order to kind of work this way out. But for now, let's see that you kind of like assume that this is working out in the same fashion, right? Now, knowing that, if you want to substitute for one thing, you have to have its derivative hanging out with the dx, right? That's why my motivation kind of goes there too. So let's say you want to substitute in the first case, in this first case, I want to substitute u as sine x. right? I want to substitute that. If I want to do that, I need to have its derivative hanging out with the dx. So I need a cos x times dx on the side. You know, just like you can't have burgers without a fry, and this is just how it's supposed to work out. So right now in my integral, I have to rewrite this, recompose this. So sine of x to the power 8 will stay there. It's all cool. I want to take off one of the cos and write it like this. Right? So I have the side dish ready with the substitution to work, right? The only thing that's bothering me right now is, of course, this is going to be substituted to be u, right? And then this is going to become my du. What the hell do I do with this? Right? So it has to either be eaten up in a substitution or just do not appear, right? And it's not doing either of those. So this is where you have to have a motivation to convert this expression, the cos of squared, into 1 minus sine of x whole sine squared. And that way, this portion will also be just a part of u. Okay? So that's what you want to do in these cases. When you have these kind of combinations happening, you want to take the side dish, compose the substitution needed, and then convert remainder into what you're going to be substituting eventually, right? So this integral after substitution would just become u to the power of 8, 1 minus u squared, du. Does everybody get that? You know, how the substitution worked and how it was framed. Right? It's very logical because there's no other way to do this, right? So that's what happened here. Let's see how would you do the same idea in this tan to the 5 secant to the 5x, right? If you want to do it that way, you got to pick what you want to substitute, right? So if you want to substitute, let's say, I'm going to write it in red because it's not going to work, so I'm going to show you both examples. I want u to be equals to tan of x. If I do that, I would need a side dish of secant squared x dx with it, right? So I can recompose this integral into being the secant to the 5 could be broken down to secant to the 3 times secant squared x dx. So now the side dish is ready, right? So now this will become a u. This will become du. How about a secant to the cube, right? We just saw that you can convert it back using the trig identity. But the identity is only for squares, isn't it? Right? I don't know any identity for secant cube. I know secant squared could be written as 1 plus tan squared x, but I don't have anything for secant cube. So this is why this fails. You cannot go this way. Not gonna work. And I wanted to show you this because, you know, intuitively you can do whatever you want in a U sub system. I wanted to show you where there's a roadblock. You know, you can't convert that. Let's try to pick the less common thing you want to substitute, right? Let's pick that you want to substitute the secant as u. Then on the side dish, you would require to have secant x tan x. Right? So now if you want to write this integral with the side dish ready, you would see this will be tan x to the power of 4 because I stripped off one of the tan from there. And it'll be secant to the power of 4 because I stripped off another one from it. And then you'll be written as secant x tan x dx. Right? And now, I know, this one becomes u. And a little bit of brain power would be required to figure out that tan to the 4 could be written as tan squared x to the squared, which could be written as secant squared minus 1 whole squared. Right? And then this, of course, becomes u. Does everybody see how this new substitution works? Right? Makes sense, right? So now when you have these kind of scenarios, you would want to make sure that you understand that it's just U substitution, nothing special. And when you look online, there will be rules telling you, okay, if this is even, that is odd, do this. If this is even, that is odd, do something else. If this is odd, do this, right? So they will make rules on this, but the motivation behind is to just have this expression working in this very specific way, right? So I don't see any need to memorize any of these formulas as long as you understand, what's going on in this whole case. So these were like the two not so common kind of things that were in this test. And there's one more question um, on the same idea. I'm not gonna give you a silent way of doing it. I'm just gonna do it in front of you on the screen. Try to follow along with it. If you follow along, I'll ask you in the very end. You just say yes or no. That's how I know that you figured out how the work is done. So here it goes. Whatever's on the screen, whatever steps I did, does that make sense? I have one yes, which is good. Does it make sense for everybody else? I have another yes, which is good. Yes. Practice is the key, right? That's why I want to give you an opportunity to try these questions yourself first, in order to be able to figure out, because you will, it's completely valid to go the other way, to do this way and then feel stuck, right? And then once you feel stuck, you develop, okay, let me try the other way too. That's something that I would not want to do, but let me try it out. Once you do that, it works. It slowly builds up, the whole thing. So today was just to talk about it. Now it's the practice, and then on Thursday we're gonna nail this thing completely and be okay with the whole scenario, right? So yeah, of course, this is where the practice is, right? The job is, because you're seeing it for the first time with me, it will take some time, but right now the objective here is for you to understand 80% of what's written, okay? And it doesn't mean that you should be able to do it yourself yet. Okay, I would love if you were able to do it, but it will take some time eventually, right? Yes, and I'm very glad this happened to make sense, right? And with that, we've concluded our discussion for today that we wanted to cover up for the coming web work. And we want to make sure that you have an opportunity to try it out first, and then we'll go over all these questions on Thursday, right? So no rush over there, and I really appreciate all the good things you're writing over there. I'm really happy. This was very helpful as well, So, and then I just wish there were more people, because then I know there are more people struggling with it. They will probably not struggle until they see the homework. And I was a student too at the same time. I had the same habit of working at the homework just like a night before and like get it done. And that's where people are going to be panicking. The group's just going to be lighting up with blah 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 blah. I need help with this. Can you help me with this? Can you help me with that? I wish they were a little bit early. You guys, you 8 of you guys were super helpful to be here with me to kind of cover these things early and learn, actually learn. During the last day before it's due, it's not learning. It's just trying to get it done way, what happens. So I want to change that thing because on the exams, that's going to bite us back, right? So that habit is not good. I struggled with it. I messed up. I don't want you guys to mess up, right? So I'm really thankful for you guys for doing your part, coming up, showing up, learning, and making efforts to learn at the same time. And yeah, so now you have a good way of starting off this homework with some actual knowledge, giving it a genuine try without being scared, because I'm going to get you through this on Thursday for sure, right? So there's no stress involved around it. All you have to do is just give it a genuine attempt, right? And once we go it on Thursday, then you will identify where you slipped. And once you identify where you slipped, the chances are you'll never slip again on those things once we fix it, right? That's how the learning is supposed to be. It has to be reinforced, right? So with that being said, I think we're done for today. If you guys have any questions, feel free to stay back and ask me. I have a couple minutes before I have to go. So, of course, I'm waiting for one of the persons to share the screen and ask a question that they had. But yeah, feel free to stay along or, enjoy the rest of your day, right? Yes, so I have a homework question there. I have one of the hands up there in the chat too. So let me just stop this recording